Welcome back to the deep dive. Today we're effectively going to ruin your appetite.
Yeah, that's almost guaranteed.
But in exchange, we're going to give you a story that is part biological thriller, part medical mystery, and honestly, part global economic case study. We're peeling back the layers of something that sits right at the intersection of marine biology and your Friday night dinner plans.
It's a fair trade, I think.
Yeah.
You might skip the sushi tonight, or at least look at it very differently, but you will understand the ocean a lot better. And once you grasp the complexity of what we are discussing, it really stops being just gross and starts being genuinely fascinating.
That is the goal. We're looking at a massive stack of research papers today. We've got clinical case reports of occupational diseases in Spain, epidemiological data from Italy and Portugal, and some really heavy reviews on the molecular biology of allergens.
Right, the component resolved diagnosis stuff.
Exactly. And all of this research centers on one specific creature. It's a creature that connects the blue whale, the tiny krill, and unfortunately, the human dinner plate.
We're talking about Anisakis simplex.
Right, the herring worm.
That is the common name, yes. But as we look at this data, herring worm feels a bit, quaint.
It sounds like something from a nursery rhyme.
Yeah, it really does. But this is a marine nematode, a parasitic roundworm that has evolved a life cycle so complex and so widespread that humans, with all our technology and our global supply chains, were essentially just collateral damage in its world.
That's a key theme in these documents that I really want to explore today. We are an accident. We aren't the target.
We absolutely are not. In biological terms, we are an evolutionary dead end for this parasite.
Before we get to the dead end part, which sounds incredibly ominous, let's just start with the creature itself. We need to visualize the threat here. If I am looking at a piece of cod or a mackerel or a piece of squid, and I am unlucky enough to spot one of these things, what am I actually seeing?
You're seeing a whitish, thread-like worm. It is usually about 2 to 3 centimeters long.
So it's not microscopic.
No, not at this stage. You don't need a lens to see it. It is entirely visible to the naked eye. In the research papers, they often describe it as being coiled up like a watch spring.
A watch spring. That is a very specific, tight image.
It creates this very tight, flat coil, and it sits inside a cyst, usually embedded right in the muscle of the fish or the gut, just waiting. It is dormant.
Waiting for what? Because this is where the circle of life concept gets a bit twisted in the sources. We usually think of the food chain as, big fish eats little fish.
Right.
But the parasite is navigating this chain with a map we didn't even know existed.
It is actively navigating the food web to survive.
Mm-hmm.
To understand the threat to humans, you have to understand the journey the worm is actually trying to take.
Right.
It starts at the very top. The definitive hosts are marine mammals. We're talking whales, dolphins, seals, sea lions.
And definitive host means that is where the worm ultimately wants to end up.
Exactly. The whale is the penthouse suite. That is where the worm becomes an adult, finds a mate, reproduces, and lays its eggs. The adult parasite lives right in the stomach of the whale.
Okay, so the whale is swimming around with these adult worms in its stomach.
And inevitably, the eggs are released into the ocean via the whale's feces.
So the ocean is just filled with these eggs?
Effectively, yes. It is a massive numbers game. Millions of eggs floating in the seawater. These eggs then hatch into what biologists call L2 larvae.
And L2 means it's the second larval stage.
Yes. These are free-swimming, microscopic little things. They can wiggle a bit, but they are mostly just at the mercy of the ocean current.
Drifting until they get eaten.
Right, they need a ride. The first victim is usually a microcrustacean. Krill, copepods, the absolute bottom of the food chain. The krill eats the L2 larva. Now, inside the krill, the larva molts. It changes form and becomes an L3.
Okay, and the papers emphasize this L3 stage a lot.
Because L3 is the infective stage.
Infective meaning it is ready to do damage.
It means it's robust enough to survive the transfer to the next host. So the krill is swimming along, carrying this L3 larva. Then the krill gets eaten by a fish. A hake, a cod, a mackerel, a salmon, or maybe a cephalopod like a squid or octopus.
This is the part of the food chain we all recognize. Fish eats krill.
Exactly. But here is the trick. In the fish, the worm does not grow up. It doesn't become an adult. It remains an L3 larva.
It's just hanging out.
It's in a state of arrested development. It migrates from the fish's stomach into the muscle flesh, curls up into that watch spring shape we talked about, and just waits.
It creates a little bunker for itself.
Yes. It creates a cyst and waits for that fish to be eaten by a whale.
It is playing a really long game. It's sitting in the muscle of a mackerel, effectively in suspended animation, hoping a dolphin comes along to snack on the mackerel.
Precisely. It needs a warm-blooded marine mammal to finish the cycle and reproduce. The fish is just a transport vessel, a parasitic host, to use the technical term from the biology papers.
And that is where we come in. We catch the mackerel. We are warm-blooded mammals.
But we are the wrong kind.
Right.
That is the tragedy here and the danger. When a human eats raw or undercooked fish containing that L3 larva, the worm wakes up. It senses the heat of our bodies. It senses the gastric juices. It thinks, finally, I'm in a whale. It is showtime.
But it's not a whale. It's a guy in a sushi restaurant in Chicago.
And that is a disaster for the worm. Our physiology is wrong. Our enzymes are different. The worm cannot reproduce inside us. It cannot complete its life cycle.
So what does it do?
In a panic, or perhaps just following its biological programming to find a better spot to attach, it tries to escape the harsh environment of our stomach.
It tries to burrow.
It digs right into the stomach wall or the intestinal lining.
And that burrowing is the first of the two major problems we need to discuss today. The papers distinguish very clearly between the infection and the allergy. I want to keep these separate for a moment because the mechanisms are so wildly different.
Good idea.
Let's handle the infection first. The official medical name is Anisakis.
Right. Anisakis is the mechanical damage caused by the living worm. This is a parasitic infection in the classical sense. The worm is physically tearing into your tissue.
The symptoms described in these clinical reports are, well, they are really unpleasant.
They are violent. You are looking at acute epigastric pain that is the upper central region of the abdomen, right below the ribs. Nausea, vomiting. If the worm stays in the stomach, this happens within hours of the meal. It is fast.
Because the worm reacts quickly to the stomach acid?
Exactly. It is trying to get out of the acid bath. If it passes through the stomach and migrates to the intestine, the symptoms might take a few days to appear, maybe 48 hours to a week.
And here is where the medical mystery part of the sources comes in. The doctors can miss it, right?
Frequently.
Yeah.
The papers actually call it a diagnostic chameleon because the symptoms, the severe abdominal pain, the vomiting, the low-grade fever, they mimic so many other common emergencies.
Like what?
It looks like appendicitis. It looks like gastric ulcers. It can mimic Crohn's disease or severe colitis.
So you might get rushed into surgery for a burst appendix.
That absolutely happens. They open you up, expecting to see a ruptured appendix. Instead, they find a perfectly healthy appendix. But a section of your intestine is heavily inflamed and swollen because your body has built a wall around a worm.
A wall?
It's called a granuloma. It's a mass of immune cells. Your immune system realizes it can't digest this invader, and it can't easily flush it out if it's burrowed in, so it just entombs it.
That is a vivid image. It builds a tomb around the parasite inside your gut.
It's a very effective defense mechanism from an evolutionary standpoint.
Sure.
The worm eventually dies inside there, but the pain, the blockage, and the inflammation can be severe until it's fully resolved.
And how is it resolved? Do you just wait for the tomb to dissolve?
Sometimes you have to, but often, especially if the pain is acute and it's caught early, the treatment is endoscopic removal. They go down the throat with a camera, a gastroscope, and a little tiny forceps.
They go fishing.
They literally go fishing in your stomach. If they can see the worm, and remember it is white and 2 centimeters long so it stands out against the pink stomach tissue, they grab it and physically pull it out.
And the relief for the patient?
Often instantaneous.
Yeah.
Once that worm stops burrowing, the mechanical irritation just stops.
Okay. That is the horror movie part of the deep dive. That's the biological thriller. But as I went deeper into these sources, specifically the molecular reviews, the second problem scared me way more. The allergy.
The hypersensitivity, yes.
Because for the infection, you need a live worm.
Yes. For Anisakis, the worm must be alive to burrow and cause that specific havoc.
But for the allergy, the worm doesn't have to be alive.
No. The worm can be dead. It can be long dead. In fact, it can be completely fragmented, disintegrated, and invisible. This is where Anisakis moves from being a medical curiosity to a serious hidden public health issue.
Let's break down the gastroallergic concept because the epidemiology papers use this term a lot.
So there is a spectrum of reactions. You can have both the infection and the allergy simultaneously. That's called gastroallergic anasakiasis.
Right.
You have the live worm burrowing, which causes the mechanical pain, and your immune system recognizes the worm's proteins and launches a massive allergic attack. Hives, swelling, anaphylaxis.
That sounds like the worst possible weekend.
It's a double whammy. But you can also have just the allergy. You eat a piece of fish. The worm was killed by freezing or cooking. It's totally dead. But you still get violently ill.
You go into anaphylactic shock, your throat closes up, you get hives all over your body, urticaria.
Exactly. This is an IgE-mediated response, immunoglobulin E. It is the exact same mechanism as a peanut allergy or a bee sting allergy.
Why, though? If the worm is dead, why does the immune system freak out? It's just protein, right? We digest protein all the time.
It is just protein, but it is a specific shape of protein that our bodies have decided is a mortal enemy. The research identifies several highly specific allergens labeled ANIS1, ANIS2, ANIS3, and so on.
This part of the research was fascinating to me. They distinguish between excretory-secretory antigens and somatic antigens. It sounded like military tactics.
It basically is biological warfare. Think of excretory-secretory or ES antigens as the chemical weapons the worm uses while it is alive. It secretes enzymes to dissolve your tissue so it can burrow. It releases chemicals to suppress your local immune system so it doesn't get attacked immediately.
Okay, so that's the live worm cocktail. That explains why the live infection triggers such a strong immune response.
Right, but then you have somatic antigens. Soma means body. This is the stuff the worm's actual body is made of. Structural proteins, muscle fibers, the gut lining of the worm itself. When the worm dies and decomposes either in the fish before you buy it or in your stomach, these proteins are released.
And this brings us to the real aha moment regarding cooking. The common wisdom, the thing our parents taught us, is just cook your fish and you're safe.
And biologically, regarding the infection, you are safe. You won't get a live worm burrowing in your gut if you cook the fish properly. But immunologically, you might not be safe at all. The papers highlight a specific protein called ANIS4.
ANIS4. This really stood out as the villain of the story. What makes this one so special?
It is highly heat stable.
Heat stable. Let's really unpack that for the listener.
It means the protein structure is incredibly tough. You can boil it, you can fry it, bake it, and the protein does not unravel, doesn't denature, it stays intact. It is also resistant to pepsin, which is one of the major digestive enzymes in your stomach.
So let's play this scenario out. I buy a piece of fish. It has a worm in it. I cook it thoroughly. The worm dies. I sit down and eat the fish.
The worm is dead, yes. But the NES4 protein is still there floating in the meat. You eat it. Your stomach acid doesn't break it down. Your pepsin doesn't break it down. It hits your intestinal lining in its original recognized form. If your immune system has been sensitized to RNES4, it triggers the alarm.
That implies you could have a severe allergic reaction to canned tuna or a fish soup that has been boiling on the stove for 3 hours.
Theoretically, yes. And the sources are quite explicit about this ongoing debate. There are case reports mentioned in the material of reactions to industrial processed foods, baby food, canned fish, surimi, where Anisakis allergens survive the intense industrial processing.
That completely changes the risk profile. It means you can't just visually inspect for the worm and feel safe.
No, you're dealing with a molecular contaminant at that point. The ghost of the worm is haunting the food.
Now, to be fair to the sources, the experts in the notes say there is some debate in the medical community about this. Not everyone reacts to dead worms, right?
Correct. It's an area of active study. Many researchers believe you need a previous live infection to prime the system. You need that live worm burrowing to get sensitized in the first place. But once you are sensitized, the dead worm allergens can absolutely trigger you. It varies wildly from person to person.
There was another protein that caught my eye because it creates a huge amount of confusion in the doctor's office. ANIS3, tropomyosin.
Ah, yes. The pan-allergen. This is a massive diagnostic trap. Tropomyosin is a structural protein found in almost all animals. It's involved in muscle contraction. But it is highly conserved in evolution.
Conserved meaning it hasn't changed its shape much over millions of years.
Exactly. The tropomyosin in a nematode worm looks very, very similar to the tropomyosin in a dust mite or a cockroach or a shrimp.
So I go to an allergist, I have hives, they do a standard skin prick test for Anisakis, and it comes up positive.
But you might never have eaten an infected fish in your life. You might just be highly allergic to the dust mites living under your bed. Your antibodies recognize the general shape of the tropomyosin protein and get confused. It is called cross-reactivity.
That seems like a massive problem for diagnosis. You could be telling people to avoid all seafood unnecessarily. You know, you have a fish parasite allergy. And the patient says, no, I just need to vacuum my house more often.
Exactly. That is why the sources emphasize component-resolved diagnosis so heavily. That's the technical term. It means doctors cannot just test for a whole worm extract anymore. They have to test for the specific, unique proteins.
Right.
If they test for ANIS1, That is unique to Anisakis. If you react to Ani-S1, you definitely have the parasite allergy. If you only react to Ani-S3, it might just be the dust mites or a shrimp allergy.
So, if you are listening to this and you have had a confusing seafood allergy diagnosis, asking your doctor for component resolved testing might be the key to figuring it out.
It is really the only way to be certain. It is immunological detective work.
Speaking of work, let's pivot to one of the most surprising sections of these papers. We usually think of food allergies as a diner's problem. You sit down at a restaurant, you eat, you get sick.
Right.
But this is also documented as an occupational disease.
Yes, this completely shifts the narrative from the dining table to the factory floor. We are talking about fishmongers, fishermen, processing plant workers, and chefs.
The term used in the papers was protein contact dermatitis.
Right. It is a sensitization that happens through the skin or through the respiratory tract. You do not have to eat the fish to get sick from the worm.
There were some really vivid case studies in the Spanish War. I want to walk through these because they humanize the raw data so well. Let's look at the fishmonger, case 1.
Right. This was a 47-year-old woman. She had been working as a fishmonger for 27 years. So a true veteran of the industry. She started getting hives and intense itching on her arms and hands.
But not all the time.
No, and that is the smoking gun for an occupational link. Her symptoms completely disappeared on weekends. On holidays, she was totally fine. Monday morning, back to the fish market. Hives.
And she wasn't eating the merchandise while she worked.
She was just handling it. The proteins from the fish and the parasitic allergens within it were entering through microabrasions in her skin. Or perhaps she was touching her face after handling the fish. She developed a type I hypersensitivity just from touching it.
And then there was the supermarket worker who had an even more specific reaction. This one felt like a perfectly controlled experiment in a lab.
The 38-year-old woman. She worked in a supermarket that rotated its staff between different departments. When she worked in the meat section handling beef, chicken, pork, she was totally fine, 0 symptoms. When she was assigned to the fish section, acute urticaria, hives almost immediately.
And the kicker was, she didn't even eat fish.
That's the key detail in the report. She did not consume it at home. She was purely sensitized by occupational contact. It proves just how potent these specific allergens are.
What about the respiratory aspect you mentioned earlier? How do you breathe in a marine worm?
You don't breathe in the worm itself, you breathe in the aerosolized proteins. Think about a fish meal factory. They dry fish and grind it up into powder for animal feed. That creates a massive amount of dust. Dust made of fish and dried worms.
That is a horrific thought to inhale.
It is a major industrial hygiene issue. Or even just a fishmonger, scaling a fish vigorously on the counter. There is splashing aerosolized spray. If you breathe that in day after day, year after year, you can develop occupational asthma.
It's almost like a biological form of coal miner's lung, but triggered by marine allergens.
It creates a severe reactive airway disease. For a chef or a fishmonger, developing this allergy is career-threatening. Imagine being a high-end sushi chef who gets hives every time they touch raw tuna or starts wheezing when they descale a snapper.
The sources mentioned a chef, actually. Case 3 in the Spanish data.
Yes, a 37-year-old male. Hand dermatitis. His hands are covered in fissures, deep cracks, and vesicles, little fluid-filled blisters. He handled squid and prawns daily. They tested him, and he was highly positive for Anisakis.
He had to wear cotton gloves under his latex gloves just to get through a kitchen shift.
Which works as a barrier, but it shows the severity of the reaction.
Yeah.
It really makes you look at the person behind the seafood counter differently. They are on the absolute front lines of this biological interaction.
It raises huge questions about workplace safety standards that go way beyond just, don't cut your finger with the fillet knife. It's about don't touch the protein.
Exactly, the invisible hazards.
I want to zoom out to the map now. The geography of this is fascinating because the worm isn't evenly distributed globally, and neither is the allergy. We have extensive data from Italy, Spain, and Portugal. It creates this Southern European paradox.
It really does show how human culture drives biology. Let's look at the data from Italy first. The Italian epidemiological study was incredibly specific about the culinary culprit.
The anchovy.
Alici marinate. Marinated anchovies. It is an absolute staple, especially in the coastal towns.
Yeah.
If you go to an Italian seaside trattoria, this is very often the appetizer they bring you. You take fresh anchovies, you bone them, and you soak them in vinegar or lemon juice, maybe add some olive oil and garlic.
Sounds delicious.
Delicious, but biologically incredibly risky. See, vinegar is an acid, but it's not that strong of an acid. It does not kill the L3 larvae, at least not quickly enough. It might irritate them, make them wiggle around a bit, but they survive the marinade.
So when you eat that marinated anchovy at the trattoria,
You are effectively eating raw, live, infective larvae. And because anchovies are so small, the larvae are very easily missed by the chef.
and the data bears this out.
Clearly. The prevalence of Anisakis allergy is highest along the Adriatic and Tyrrhenian coasts, places like Pescara, where this specific culinary tradition is deep-rooted.
But the paper noted a distinct shift. They called it the sushi effect in the inland cities.
This is where modern globalization hits the epidemiological data. In landlocked cities like Milan and Turin, the allergy rates are rising sharply. And these aren't old fishermen eating traditional marinated anchovies. These are younger people, urban professionals, eating sushi and sashimi.
So you have the traditional risk, the anchovies, and the modern risk, the sushi, converging in the exact same population.
Exactly. It's two completely different culinary routes leading to the exact same parasite.
Now, compare that to Portugal. This is the puzzle in the papers. Portugal has one of the highest fish consumption rates per capita in the world. They eat massive amounts of seafood.
You would naturally expect them to be the allergy capital of Europe. If high exposure equals high allergy rates, Portugal should be off the charts.
But they aren't?
No. The reported rates of sensitization are surprisingly low compared to Spain or Italy.
Why? Is it the type of fish they catch in the Atlantic?
It's the cooking method. Think about classic Portuguese cuisine. Acalo, salt cod.
Which is salted and dried for months.
The extreme salinity and the desiccation kill everything. Nothing survives that curing process. And then how do they eat their fresh fish? It's almost always cooked. Boiled potatoes with boiled fish, deeply grilled sardines. They do not have the same deep cultural history of eating raw flesh like the Japanese or lightly marinated flesh like the coastal Italians.
So the simple cultural habit of boiling or heavily salting fish essentially saved them from the epidemic.
Historically, yes. But the Portuguese source includes a very stark warning. They say, this is changing. Sushi bars are opening all over Lisbon. Ceviche is becoming incredibly trendy. They predict the Portugal paradox will completely disappear as their diet globalizes.
So as they adopt global food trends, they adopt global parasites.
Precisely. The biology follows the culture.
There was one very practical tip in the Portuguese paper that I think every single listener should memorize right now. It was about which part of the fish to eat.
Ah, the ventral tip. This is basic anatomy for diners. Remember where the worm comes from originally in the fish. The gut.
Right. It lives in the stomach cavity of the fish.
When the host dies, when the fish is pulled onto the boat, the worms panic. The temperature of the fish drops, the internal chemistry changes. The worms migrate out of the gut cavity into the surrounding muscle tissue. Where is the closest muscle to the gut?
The belly flaps.
The ventral region. In sushi, that is often the toro, the fatty belly cut of the tuna or salmon. It is the most delicious prized part, but statistically it carries the absolute highest parasite load.
So the most expensive fatty cut is actually the riskiest cut.
Unfortunately, yes. The tail muscle, the caudal region, is much further away. It takes the worm a lot longer to migrate through the dense muscle to get there. So, generally speaking, the tail is a safer bet than the belly.
That is news you can use. If you are worried, ask the sushi chef for the tail cut. Or just avoid the belly altogether.
It lowers the odds. It certainly doesn't eliminate them entirely, but it is a statistical help.
Which brings us to the most important section, safety and prevention. We've scared everyone sufficiently by this point. How do we actually kill this thing? Because I assume we aren't going to tell people to stop eating fish.
No, and we shouldn't. Fish is incredibly healthy. It's a great source of protein and omega-3s, but we need to follow the golden rule of prevention, which is temperature control. It is the only guaranteed weapon we have against the nematodes. You have two choices, burn it or freeze it.
Let's talk about freezing first, because that is the standard for sushi. We hear the term sushi grade thrown around all the time at the grocery store. Does that term actually mean anything scientifically?
It's a marketing term, mostly. There is no official government inspector stamping sushi grade on a piece of tuna like they do with grade A eggs or USDA beef. But the regulations behind safe raw fish are very real. In the EU and in the US under the FDA, if you serve fish raw in a commercial restaurant, it is legally required to be frozen first.
And we aren't talking about throwing it in my kitchen freezer next to the frozen peas.
Definitely not. Your home kitchen freezer is likely sitting around minus 15 degrees Celsius, maybe minus 18, but it fluctuates constantly. You open the door to get ice, it warms up. To kill Anisakis, you need what they call a killing freeze. The FDA standard is minus 20 degrees Celsius, which is minus 4 degrees Fahrenheit, for at least 7 full days. That is a long time.
Or if the restaurant is in a hurry.
Or Speed the process up, minus 35 degrees Celsius, minus 31 Fahrenheit for 15 consecutive hours. This is usually done with heavy industrial blast freezers.
Why does it have to be so incredibly cold?
It's all about ice crystal formation. You need to freeze the water inside the worm cell so hard and so fast that the sharp ice crystals physically rupture the cell membranes. If you freeze it slowly or not cold enough, the worm might just go dormant. It is essentially cryopreservation. You thaw the fish on the counter, and the worm wakes right back up.
That is remarkably resilient.
They are ancient survivors. You need to shatter them at a cellular level to be safe.
What about heat? If I'm cooking the fish at home on the stove?
You need to reach an internal temperature of 60 degrees Celsius, which is 140 degrees Fahrenheit, for at least 1 minute. Though cooking it at that temperature for 10 minutes is the safest bet to ensure the heat penetrates evenly to the core.
60 degrees. That is a thoroughly cooked, opaque piece of fish. That is not a seared tuna steak with a cool pink center.
No. If you are eating tataki, where it's seared hard on the outside but raw in the middle is still a massive potential danger zone. If a worm is coiled up in the center, it's just getting a warm, comfortable bath.
And we have already established from the Italian data that marinating, pickling, and cold smoking are not safety measures at all.
Correct. Cold smoked salmon. The process doesn't get hot enough. The worm survives. Pickled herring. Unless it is heavily, heavily salted for a very long time to fundamentally change the osmotic pressure and dry the worm out, it survives.
Are there any loopholes in these regulations? Is any fish naturally safe to eat raw?
Safe is a strong word, but there are definitely safer categories. Farmed Atlantic salmon is the big one highlighted by regulators.
Why is farmed safer? Usually people assume wild-caught is the premium, cleaner product.
In terms of taste profile or ecology, maybe. But for parasites, farmed is vastly cleaner. It all comes down to diet. Farmed salmon are raised in pens and they eat processed pellets. Feed that is heat-treated during manufacturing. They do not eat wild krill.
And if they don't eat the infected krill, they don't ingest the L3 larva.
Exactly. You break the circle of life. The FDA and the EU actually grant specific exemptions for aquacultured fish that are fed on parasite-free diets. They don't strictly require the freezing step for those fish because the risk is considered negligible.
That explains why supermarket sushi is almost exclusively farmed salmon.
It is consistent, it's cheap, and it's parasitologically clean. It's a completely controlled environment.
What about tuna? I read in the sources that tuna is sometimes exempt from the freezing rules, but they definitely eat wild prey.
Tuna is the complex, controversial exception. Certain large species, like yellowfin and bluefin, are often exempt from the mandatory freezing requirement in high-end markets. The logic behind the exemption is partly biological. They are pelagic, open ocean hunters. They don't hang out near the bottom or the coasts where the infected crustaceans are as dense. Some older data suggests they have lower parasite loads in their muscle tissue.
But it's also partly economic, isn't it?
It is a huge economic pressure. Freezing a $50,000 bluefin tuna changes the cellular texture slightly. The high-end market demands fresh, never-frozen fish. So, regulators often allow a visual inspection by a trained chef instead of a blast freeze. But let's be totally honest, visual inspection is highly imperfect. The larvae can be buried deep inside the muscle block.
So, eating fresh, never frozen wild tuna at a fancy restaurant carries a non-zero risk.
It does. It is a calculated risk that the diner takes.
So if I want to make ceviche at home this weekend, what is the protocol?
Do not go to the seafood counter. Buy the fresh wild catch of the day, take it home, and squeeze some limes on it. That is culinary Russian roulette.
What should I buy instead?
Buy the frozen block. The stuff that is rock hard and vacuum sealed in the freezer aisle. It has likely been blast frozen on the commercial ship the moment it was caught, or at the processing factory, to temperatures your home freezer can never reach. It is the absolute safest way to prepare raw fish at home.
Frozen is best. It goes against every foodie instinct we have been taught.
In this specific parasitological case, yes. Frozen is infinitely safer.
We have covered a massive amount of ground here today. We've gone from whale feces to molecular proteins to Portuguese kitchens to the frozen food aisle.
It's a very wide net we cast.
If you had to distill all of this research down for the listener, someone who loves seafood but is now looking at their lunch with deep suspicion, what is the ultimate big takeaway from all these sources?
I think the main takeaway is awareness, not abstinence. You don't have to stop eating fish. It's a vital food source. But you need to understand that it is a wild product. It comes from a complex ecosystem where parasites are the absolute norm, not an anomaly.
We aren't eating a sterile, manufactured puck of protein. We are eating a slice of nature.
Exactly. And nature includes Anisakis. So just recognize the risks. If you have a weird, unexplainable allergic reaction after dinner, don't just brush it off and don't just assume it was the shrimp. If you work with fish professionally, protect your skin and your lungs. And above all, respect the freezer. The industrial freezer is your best friend.
I want to leave the listeners with a final thought that struck me while reading the introduction to that heavy molecular biology paper. We tend to view ourselves as the absolute masters of the food chain. We harvest the ocean, we control the menu, we act like we are totally apart from the biological system.
We certainly like to think we do.
But to Anisakis, we are just a trap, a biological mistake.
We are a dead end.
But as our global supply chains get faster and faster, getting a fresh salmon from the waters of Norway to a dinner plate in Tokyo in under 24 hours, we are systematically bypassing the natural barriers that used to protect us. Time and distance used to kill these things. Now we are overnighting them directly into our sushi bars.
That is a profound point. By eliminating the spoilage time that naturally killed off the parasites, we are keeping the parasites incredibly fresh, too.
Right. Are we unwittingly inviting these hidden guests into our immune systems by being just too efficient with our logistics?
It's entirely possible. Our modern efficiency is their new opportunity.
Something for you to chew on.
Yeah.
Very carefully.
Very, very carefully.
Next time you are at the sushi bar, maybe give a little nod of respect to the complex biology sitting on your plate, and then politely ask the chef if it was frozen first. Thanks for diving deep with us today.
Stay safe out there.
See you next time on The Deep Dive.